void here, you have some like a hole, and the fluid has to go in. Yeah, because it's measured whatever after the void, and you have the detector above that one. So if you have in turbulence flow regime, that's fine. But if you are in the segregated laminated, you don't write this because it just measures whatever the fluid in the void. So it's based on the electron density and etc. So yeah, if you have gamma ray scale, high gamma ray scale, be careful. It might interference with the gamma ray detection. Yeah, but as far as I received the data, it was okay. Even you have a big scale, gamma ray scale, but yeah, because this one is just measuring whatever in the void, so it was okay. It's not measuring what is outside or beyond the tube. Or, yeah, radioactive decay, so statistical variation, yeah. So the top one detector is just a standard gamma ray sensor. Uh, yeah, this is the old times weather product, it's been long time. But usually the void is not that big. The correction is something like this. So this is coming from Sonderling. From 0 to 1 is a bit straight line, but from 1 to 1.2 is another slope. So be careful when you deal with the brine, like high salinity, and you make sure you don't have only 2-point but 3-point calibration. You have salt water, fresh water, diesel, or gas. So you might have more point and then you'll be reading correct. Otherwise, your reading will be a lot bigger in salinity and in saline water. Okay, so it depends on the hydrogen index, scattering, etc. So, that's the FDR. Yeah, so the statistical is like gamma statistical. I'm not sure about the half-life of this americium. I think it's a bit quite long. If I'm not wrong, it's 20 years, something like that. So you can keep quite long for the source. But after sometimes, the statistical, the radioactive count will be smaller. So then the reading of your gamma ray will be more spiky or more noisy. So be careful on that one if you have quite old radioactive materials. But then you need to calibrate first. That's fine. So that's now is FDD or DFD you're tuning for. They have different mnemonics from different companies. So basically, it's like the one on the left. Usually, you have some cages to prevent the debris or whatever to get it into the sensor. It's quite sensitive. It's sensitive. So it's just based on the frequencies changes. Yeah, it's based on the vibration. Usually, this one used for liquid only, but nowadays you can use it for gas as well. On the bottom right, you might see this one is you have different color. You have a different settings there. So, for example, you are in zero point 0.6, right? 0.6 gram per cc. For example, you are in the oil. If you are in 200 degrees, you might get about 1550 hertz. But if you are in 100 degrees, so it's about 1600. So it's already 50 hertz difference. Yeah. So be careful on that one. It's just pretty sensitive with temperature. But you should be able to be adjusted in Vario when you acquire it. Yeah. Or you can just recalculate when you have the memory. So what we receive is not the frequency. What we receive is already the gram per cc. So in Emerald, we don't correct for temperature.
Oh,
It's
like
totally done.
water hold up. that we.
No, it's different. Water hold up is the conrate, right? The CPS we receive from capacitance, but from density we get on already the camera. Sorry, gram per cc. Yes.
Oh,
So we don't get the raw data. So it should have been done in Warrior.
okay.
Yeah, we can do with some calibration, but it's better to be on acquisitions. DPTC core, we know already this one. Yeah. So DPTC core is corrected for deviation, but both still need to be correct for friction. Why we cannot correct in this first time? Because friction, you need to have velocity. So I need to pay in this rate calculation. So we need to get it. But for correction deviation, we know the angle, we just put it. Okay, density give instant picture. Yes, slowest pass. Well, depend, yeah, of course. So just constraint PPD density, we know that one already. Look for changes indicate and raise different rate. Yes, why not? Some is confusing reading because it's not represent the density of the produced fluid. We know that one. Accuracy resolution, sometimes you can see the number here is amazing. It's pretty good, but actually it's really depend on the in the field. Yeah, it's not really like this. In theory, it's pretty accurate. We might see some calibration, etc. They might not be very accurate at the end. So QUAQC, yeah. If it is fluency, we need to, I mean, we need to know which mnemonic will be coming in when we load the data. So we choose accordingly. If we have those three, that's fine. Just load everything in and then we define as they are. In rough casing roughness, we talk about that. Well angle, yes. So we need to get well angle. If it is vertical or 10 degrees, so we don't really care about that much. Highly deviated, we need to get the angle correct. Compared with DPTC, as we haven't done it because we don't see it as Emmanuel was asking whether FDI, FDD or DPTC, which one is the best one? The DPTC is coming from the pressure. Pressure usually is master calibrated, so it should be pretty good. And DPTC is the accuracy is good, but the resolution might not be because it's just fluctuated, yeah, depend on the pressure in the wellbore. But FDD, FDI is really depend on the calibration. So the absolute number might not be correct, but the relative number or yeah, vertical resolution is a lot better than DPTC. So you can combine. Jetting effects, we might see. Yeah, we don't use it for calculation, of course. Nuclear tuning fork, yeah, check quality, whatever. It's just combine with the capacitance if you can see, or you can compare density with the DPTC per meter. So if you have a lot of more than one reading, that's good if you can compare. But be careful, sometimes they are not confirming, but the more different tools, it might not be confirming. So we need to choose which one is the best to be used for calculation. Check for repeatability. Yes, of course, we know this one. Statistical error on the radioactive stuff. Capacitance. So we call it water hold up because it differentiates between water and non-water based on the capacitance of the fluid into the, what you call it, the chamber, whatever in the tool there. So we have an axle in the middle and you have the tool body and you just measure the capacitance between the axle and the tool body. So it's like two, what you call it, two probes. So in between the probes, we'll calculate the capacitance. So it's not the same like resistance. Almost the same, but it's not really the same. Resistance, if you put the voltage, will be resist to get the, what you call it, the current. So it's on low. But capacitance is like, I don't know how to call it. It's like how good the material to keep the voltage to keep the electric. So then you can discharge. So if the capacitance is good, they can keep quite a long time. But if capacitance of the medium is not good, so it's just keep very short time and then release. So it's like keeping things. But the resistance is just the rest. Almost the same, but it's less. Um, you can see this one as well. We look at yesterday, but then X and Y is different direction. So the frequency is on the Y, the output is on the X here. So you might see below maybe 50%, yeah, below 50%, you can have quite high change. So from 1900 to 33, 19,000 to 33,000. So quite high. It's 14,000 different for 40% hold up. But from 40 to 100%, you might just look at 2,000 frequency change. It's still there, but it's not that sensitive. So capacitance will be very sensitive in low water holdup. In high water holdup, still can measure, but it's not that sensitive. It doesn't mean it doesn't work. It's just not sensitive. This is the one like this. So you might have 2 windows or 4 windows or 6 windows. There are different type of tool, but the principle is the same. So you have the axle and you have the two body. You measure the medium in between those two electrodes. And yeah, we need to have a surface check, but again, we need to get the downhole in situ calibration. Yeah. You can compare surface check before and after, but what we use in Emerald is the one at downhole in situ. Something like this, yeah. We don't see this one yesterday, but what we see is the one here, the water wetting. The water wetting effect. Okay? That's why we like to have the down pass rather than the up pass for the capacitance in order to get rid of the water wetting. So we did already there with the normalized response. We need to choose the capacitance tools and we need to choose the correct tool because the different tools here have different plot for correction. And then you need to put two numbers there, 100% water, 100% hydrocarbon, which is, we get it from the lines yesterday, the red line and the blue lines. You can type in or you can use with the mouse. Okay, resolution is something like this, 1%. This makes sense. Yeah, you can see this one. The accuracy is 3%, 5%. So it's not really accurate like the density. Density was pretty accurate, but yeah. Capacitance. Okay, we do repeatability, of course. Okay, we know this one. Slow down fast, yeah, you might do, but can check which one is the most consistent data. So passes use hold up. I think they don't use it anymore. This is from Halliburton, but it's belong to Sondex at the moment. This is Cobalt 57. Principle is almost the same like open hole density too. Yeah, the same. So yeah, it's radiate gamma ray around the tool and moving back into the sensor detector. The difference is with the FDR. On the FDR, you like to get the fluid in between the detector and the source. But in this GHD, you might have some tungsten piece. So we don't want to get gamma ray propagate in the tool body. It has to go out, interact with the hydrocarbon or electron in the fluid in the wellbore and coming back there. Yeah, so it's a bit different on that one. But still it's high, low energy gamma rays. It's still the gamma ray what you call it, source. Yeah, it's affected by the IP. So it's really like a gas and liquid. So you might see the gas and liquid. The difference is pretty big in the big casing, but in small casing, not really. This one you can see this. It's just a combination of all the stuffs. Cause hold up, I think just leave it like that because we never run this one anyway. The GST. And yeah, GST you need to have something. This is from window, radio window. So you need to correct for the PVT, you need to correct for the temperature, pressure as well. So a lot of correction. And at the end, it's not accurate. Uh, okay, so that's it. So that's the tool, yeah. FDI, FDD, in term, what you call it?
GHT.
Yeah, GHT. So what else?